Hi, we are Group B6. My name is Jacqueline Miller, and my group members are Guy Lynn, Mike Manzano, and Sean Dallasman. And today we will be talking about function growth and analysis for runtime. So first is time complexity. The time complexity of an algorithm can be expressed in terms of the number of operations that an algorithm uses when the input has a particular size. It is expressed in the number of operations required because different computers need more or less time to perform basic operations depending on the type. Another complexity is worst case complexity, and this is an algorithm that means that the largest number of operations required to solve a problem using the algorithm on an input of the specific size. It tells us how many operations an algorithm needs in order to guarantee that it will produce a solution. So there are different amounts, but it just has to produce some kind of solution to discover the algorithm. Here displays the growth of the functions used in big O estimates. As you can see, there's log n, there's O of 1, O of n, and it increases and increases. And on the next slide here, it shows that O of 1 is less than O of log n, and then it goes all the way to O of n factorial, which is very, very big. Here are some commonly used terminology. There's just of different types of complexity. There's constant complexity, logarithmic, linear, polynomial, exponential, factorial, all these different ones that can be used to calculate algorithms. In the computer time, the most famous ones are n and 10. Okay, so here's the process that usually you go through to calculate a time complexity and to find the maximum element in a finite solution. So there's a procedure, you're given the max, and then a for loop. Here is I from 2 to n. Then you have an if-then statement, and you return the maximum largest element, because that's what you're trying to find. But remember that the number of comparisons is used to measure the complexity, because comparisons are the basic operation used. So looking at this, if we actually do it out, you can get the function given in the previous slide uses the variable max as a temporary holder for the first element in the finite solution. Oh, as you see, there's a max and value there. And then for the for loop, it iterates through the sequence. There's for I, you can 2 to n, but it really can be anything that's just through that sequence. It can be 1 to 10 or whatever's there. With each iteration, the control if statement compares the max to the next element in the sequence, and you keep on going. So if the max is less than the next element, then that updates the max to hold the value of the next element, and then it iterates through the for loop to keep making the comparison. So you keep on going. You want to go to the next one. If that one's less, that means that the one that you're comparing to is bigger, so you want to go to the next one and see if that one's less than. If the max is greater than the next element, max keeps the same value and goes through the for loop again to compare the next element in the sequence. Since the algorithm compares the max to the next, there are 2 comparisons used for each iteration from 2 to n. This means that there's 2 to the n minus 1, and then plus the next comparison, which is 2 to 2 times n minus 1 comparisons for this algorithm. Here's an example of worst case complexity of a linear solution search. So again, it's similar to the one before. There's a procedure, and you have the I, which is the initial value, and then this uses a while loop and contains an if-then, and then an else statement after, and then you return the location of where the term is. Now okay, here you can see that since n grows linearly, its worst case complexity would be having the search visit every single element once. In this case, the value being looked for is either the last element in the list or not in the list at all. Thus, the worst case complexity is theta n, big theta n. Here's an example used for the worst case complexity of a binary search. So, binary search, just through a number of integers, a to n, in increasing integer order. You start with I, which is the left endpoint of the search interval, and j, which is the right endpoint. So the interval is from I to j, and that equals 1 to n. So while I is less than j, you have an element L that equals I plus j divided by 2, which is usually, that basically means you're splitting the sequence in half, and you're comparing each part. So if x is greater than a to the m, then I equals m plus 1, else j equals m. X equals a, then the location is I, and then else the location is 0, and then at the end you return whatever location you found. So the while loop checks to see if I is less than j. Within the while loop, the integer x being searched for is compared to the middle term of the interval I to j in this situation. If x is greater than the middle term, then I is updated to the middle plus 1 term, else j is updated to the middle term. The interval is decreased in the while loop, keeps iterating until I is no longer less than j. And then also if x equals the location at I, then the location is just obviously I, and if not, then the location equals 0. So there are 2 comparisons used initially for the list, and then after that 2 more comparisons are used when the list has been reduced to 2 to the k minus 1 terms. And then after that, there's 2 more. You keep on going 2 to the k minus 2, 2 to the k minus 3 elements until it's been reduced to just 2 terms, 2 to the 1. With 1 term remaining in the list, one comparison checks if there are other terms left, and another comparison checks if the remaining terms is equal to x. Therefore, there's 2k plus 2, which equals 2 to the log n plus 2 comparisons required. So the binary search algorithm uses O log n comparisons in the worst case. If you want any more videos or information, you can go to www.knowadams.com for more discrete mathematics problems.